sequence. Okay, so in this chapter, this is the last of the chapters that are going to be based off of, big ideas. After this chapter, we're going to be going into specifics. So like the next chapter is respiratory diseases. Chapter after that is skin diseases. So this is like the last one that we go over the big ideas of things that actually pertain to all the different types of pathogens. And so what it is antimicrobial medication. So I consider this kind of like a pre-pharmacy chapter. You'll have to take, for those of you wanting to get into nursing school, you have to take pharmacy classes there too. This chapter here will help you at least with some of the basic understanding of how we develop drugs. So the first thing here, of course, always history. So we have imagine the world without antimicrobials. Well, reality is we've only had antibiotics since about the 1920s or so. Before that, just a simple cut could be the end of your life. If you ended up getting an infection that ended up going septic. Nowadays, we have medicines out there that we can pretty much fight off most of that. But then we see things like antibiotic resistance. So in this chapter, we'll also cover some of the ways that antibiotic resistance comes about and how we can actually continue to battle that too. So discovery antimicrobial drugs, we have Salvarsan was the original. It was built by a man named Paul Ehrlich in 1910. This was the first documented case, but he really wasn't after an antimicrobial. It was just an accidental find. The next one, Protozol, Gerard Domrich had discovered this one while trying to treat streptococcal infections in rodents. It had no effect in the test tubes, which was curious. So when you actually would try to kill the bacteria like in a test tube with this particular drug, the bacteria just survived. And it was like, well, how is it possible that you have a drug that works well in the animal, but not in a test tube? And so through that process of understanding or trying to understand how this drug worked, they realized that it was actually an enzyme inside the body that was actually cleaving that drug to make it active. And that was a very novel find for them back in the 1930s. Nowadays, we understand that enzymatic reactions do a lot in terms of how pharmaceuticals are used inside the body. And so these were the first two, and that one actually became our first sulfa drug. And so we'll talk about sulfa drugs as we move forward too. So both of these are chemotherapeutic agents. And so unfortunately, there's this preconceived notion that when we use the word chemotherapy, what do we think about? Cancer, right? But in this case, that's just cancer. When we use the word chemotherapeutic, we're saying that we're using some sort of chemical to treat the disease. And so these are molecules, chemicals, whatever it might be, that we're going to be using to treat that particular disease. And so when we use the word antimicrobial, we're specifically talking about a chemotherapeutic that's used against microbes. All right. So just terminology and changing your thought patterns of what you may have thought these words meant compared to what they actually mean in the medicine literature. So soon after, these two gentlemen actually came up with these novel drugs. It was Waxman purified streptomycin. And so if you took the 210 class, we actually have an entire chapter dedicated to this particular genre of bacteria. They're the largest group in terms of their size and in terms of all the equipment that they have, virulence factors, different onboard genetics that they may have. And that's actually where we get most of our antibiotics. They have so many different weapons to help them fight off all the other prokaryotes that might be living next to them, that we just simply go out and look for them, find them, see what they produce, and see if there's some sort of medicinal benefit to them. And so this is really where most of our antibiotics come from. So second bullet point there, even today, pharmaceutical companies examine soil from all over the world. We're still discovering, if you ever pay attention, usually about once a year, they come up with the new organisms that have been discovered that particular year. And there might be a couple macro fauna and flora, ones that we can see with our eyes, but for the most part, it's usually microbes, and to the tune of thousands. And so if we're finding all these new microbes every year, it's bound to find new medicines too. And so it's a big deal for us to look for these new organisms to help find some of these new medicines, because instead of reinventing the wheel, which would be really what you're doing at a laboratory setting, using what nature's already provided us is always going to be the easier route. when we think about the genetics, somebody asked me this the other day, I was out and about, somebody asked me, well, how close do you think it is to finding artificial or be able to build artificial life? Well, Hollywood's got it, where they make it sound like it's going to be easy. But when you realize that for every spot in the code, right, there's the possibility of 4 nucleotides. You got G, T, A, or C that can go in there. And then you figure that each protein, usually, a single protein is tens of thousands of nucleotides long. You're looking at a astronomical change, right? You're looking at tens of thousands of possibilities. Each one may be one of 4 different nucleotides. The idea of actually trying to build anything by hand is nonsense. It's just not going to happen. Yeah.
So what about like in Japan, how they have like the robots that they can't do much. They can do some stuff, like some human.
Mm-hmm.
So would that tie into that?
Well, that would be artificial life in that kind of component, but you're actually looking at it from a medicinal, and actually making a new drug. That's usually, these drugs are protein based. That means they have to have a DNA component to them. They actually go into the lab and say, well, we're just going to build a new drug. There's no way that we can actually make that happen. Can I do it with machines? Sure, I can tell the machine to make me a sequence of DNA that's GGCC. No, we're just not going to. No, well, even then, getting it right is impossible, right?
The machine couldn't do it?
The machine wouldn't be able to come up with an idea of what it should look like, right? It'd be really difficult for us to actually go from just saying, let's see what happens when we combine these nucleotides together. So instead, what we do is we go out and we search for new microbes and see what they actually already produce, because they're producing it to protect their niche. They're using it to protect their living space. And so if they have a different type of protein that they've made that fights off gram negatives that might be living next to them, well, then maybe we can use that as a new possible drug. And then we can modify it from there. You can always tweak things pretty much. You just can't go build it from hand. So that's why this is big. This is why this particular slide is big, is it's showing you the basically the phylogenetic tree, but from the standpoint of antibiotics. Every single one of those antibiotics, every single one of those branches is a different antibiotic, and shows you possibly where they came from in terms of all originally yielding from this penicillin strain. And so when we think about these different drugs, a lot of them actually all relate back to penicillin. And so we'll see that as we move forward also. So first we got to look at the antimicrobial drugs, and we have to think, how beneficial are they? So if I have a drug, maybe as we were just talking, I have something that we just discovered, and it is gangbuster. It kills everything around it. But when I put it into a rat, it kills the rat too. Is that a good drug? Nope. So that's what we're talking about there, selective toxicity. The cause greater harm to the microbes than it does the host. Right? We want to make sure that we're selecting the toxicity where it destroys the microbe and minimalizes any sort of issues with the actual person that we're giving it to, or animal. And so we don't want it to interfere with any of the structures inside us, but we certainly want it to interfere with the microbial structures. So the very first things that we're going to look at, the very first class of drugs, once we get into them, are going to be the cell wall synthesizing molecules. So why is that great? Because we don't have cell walls inside us besides our normal flora. The human body doesn't have cell walls. I tried to explain that to my 143 class. When you don't have a cell wall, well, then that makes a good target for a drug, right? We go target cell wall, there's going to be no toxicity to us for the most part. And so we relate this as what's called a therapeutic index. The therapeutic index is going to be the lowest dose that's toxic to a patient is going to be the dose that's used in therapy. So what we do in part of the studies I've been part of is that you dose an animal. So you might give them 50 mgs, 100 mgs, 150, 200, 250, 300. You're testing them, and you're trying to see where is that range where you get the highest amount of death in the microbes, yet the lowest amount of toxicity to the animal. And you're trying to find that crossroad. And that ends up being where we make a therapeutic index. And so that will be, after multitudes of testing and ensuring that that number is correct, we'll then use that number as the suggested dose to a person. And so we're trying to find that number. Now, there's 2 different types of antimicrobial actions that drugs can take. They're going to be bacteriostatic. Bacteriostatic is that they stop the growth. It doesn't kill the ones that are already there. It's going to stop any new growth. And then bactericidal are going to kill all bacteria. So why would bacteriostatic be important? Because if we stop the growth, remember bacteria grow they can double their numbers every 20 to 30 minutes. If I can stop that, then the immune system will come and clean up the rest. But if the immune system's constantly being overwhelmed by new numbers that are always showing up every 20, 30 minutes, then the immune system's going to have trouble actually catching up. And so sometimes bacteriostatic drugs are just as good as bactericidal, sometimes even better, because they don't do as much harm to your normal flora. If I'm doing just stopping new growth, well, your normal flora will stay mostly intact. But I'm also stopping those pathogens from growing too much. If I do a bactericidal drug, I'm wiping them all out, and that could potentially cause secondary issues. So then we actually talk about the spectrum of activity. So we have broad versus narrow. So broad spectrum is that they wipe out everything. They affect a wide range. This is going to be important in treating acute illness. So somebody comes in, they're sick, they got some sort of infection, but we have no idea what's actually causing that infection. We're going to give them a broad spectrum antibiotic first, because we just want to try to stop whatever it is that they have.
So if someone had like a surgery and their white blood cell count is like now
astronomical.
Really it's like raising really high, and they don't know exactly what it is because they're waiting on like the cultures or whatever. You would give them the broad spectrum antibiotic just to
usually in an IV too.
To try to settle whatever is going on.
Mm-hmm. Yeah, because we want to get it out of the blood, so we'll put it in an IV to make sure that if it did get into the blood, that it's at least trying to clear it down.
When something becomes in the blood, like it becomes septicemic or septicemic, can you get rid of it? Can you get it out of the blood?
You can, but
so it's not always lethal.
It's not always. My mentor survived it last year, it can be. It just definitely becomes more dire. It becomes more dire, if you end up getting it septic. So broad spectrum are going to be important for that initial, we don't know what it is. We're waiting for med tech to come back or pathology to come back with whatever the particular, microbe is. And then when we get that, then we're going to do a narrow spectrum if there is one available. There's not always something available, right? So in this case, narrow spectrum antibiotics are going to be the ones that focus just on what it is, or what class of bacteria that is the current pathogen in that patient. And so they're going to be less disruptive to the normal microbiota compared to the broad. And so then we can treat specifically. It's sort of like more putting a laser target on the pathogen versus just wiping them all out, which is going to affect the normal flora too. So broad, good. Like we were talking about the other day, ciprofloxacin that I take with me when I go overseas. Ciprofloxacin is a broad spectrum because, again, you don't know what you got infected with. Just take that broad spectrum to make sure that you wipe it out. Narrow spectrum, going to be a little bit less toxic issues in terms of wiping out the flora, normal flora. All right, so sometimes we do combinations. So how many times you've been prescribed more than one drug at a time? A lot of times you get 2, 3, 4, some depending. So we have to think about the effects of combination. So there's 3 terms here. Antagonistic is when the drugs interfere with each other. This used to be really problematic up until the last decade or so, because if you went to one pharmacy and got your drug filled and you didn't tell the second pharmacy, maybe it was more convenient one day to go to a different pharmacy to get your other drug filled, they didn't know what the heck you were on. And there could potentially be antagonistic effects. Nowadays we have more computerized systems, mainly because we're trying to fight off drug addicts and things like this. Go in and try to get multiple prescriptions, but also it's there for a beneficial purpose too, to ensure that the drugs that you have been prescribed already don't interfere with the ones that you may be getting, or the ones you're getting aren't going to interfere with the ones you already have, right? So that's antagonistic. We don't want that. We don't want the drugs to antagonize each other. Combinations where one drug enhances the other are synergistic. Right. So in this case, we're doing, there's a lot of different drugs out there you might see commercials for. Oh, well, if you're already on this drug, ask your doctor about adding this one too. Well, those are going to be synergistic ones. They're ones that are designed to help or boost the effects together versus taking them individually. And then let's say you're on an antibiotic and you're also on a blood pressure pill. Those are going to be additive. That means that they have absolutely no cross reactivity to each other. It's just that you're taking more than one drug, right? So the worst of them are antagonistic. If there is a possibility, to get a synergistic drug, sometimes those are helpful. And then most of the time, the drugs that you take are going to just be additive. They're just going to be doing something else, and they're not actually going to interfere with each other. All right, so then we got resistance, right? We get all these antibiotic-resistant bacteria out there. Very scary, can be, especially if you work in that setting. Certain bacteria have innate or intrinsic resistance. So when we think about the innate immunity from chapter 14, that's what we're born with, right? That's your skin, your mucus, membranes. You got the, many of the different things we talked about there. Well, when we're talking about a bacteria's innate resistance, these are things it's basically already has, right? It's not something that it developed. And so in this case, something like penicillin, we're going to get into it here as we keep moving forward. Penicillin is a drug that blocks the cell wall synthesis, specifically blocks peptidoglycan. Well, penicillin is completely useless to something like Mycobacterium tuberculosis because its name myco tells us it has mycolic acid and not peptidoglycan. So even though Mycobacterium tuberculosis is a bacterium, I can't give penicillin because penicillin is only going to affect the peptidoglycan. It doesn't have peptidoglycan.
So will it affect it won't affect anything with the prefix of myco?
Yeah, myco, anything with myco in it, so it won't affect it. So penicillin's a useless drug to give. So that's why it's also important for those of you that want to start working in clinical settings that you understand these drugs and understand their modes of action. Because, again, doctors, they're good, but a lot of times they're going to be doing their rounds, right? And they may only see that patient for a few minutes that day, and the rest of the time is spent with you. And so I'll tell you another story. One of my best friends from high school went in, emergency appendectomy. They put her on an antibiotic. She said that she was allergic to penicillin. And when I went in to see her, she had all the signs of inflammation, had all the signs of an allergic reaction. And they were just telling her it was because of the post-surgery, wooziness and whatnot coming out of it. And I was like, I don't think so. I said, that looks like a allergic reaction. And I said, I looked at the bag, and it was a brand name. And the brand name, when you actually looked up what the brand name was, it was a penicillin derivative. I went to the nurse in charge, and I said, she's allergic to penicillin. Well, that's not penicillin. Well, who are you? Well, I wasn't about to explain the difference between a PhD and an MD, so I was like, I'm Dr. Coleman. She's like, well, this is what they prescribed her. I was like, but your job is to know that she's allergic to penicillin and to recognize that drug is a penicillin derivative. And she apologized, said, we'll make sure we switch them. Her husband and I went to go get some dinner, come back, they put her on a brand new bag of the same thing. Yeah, I'll get you fired if I find out that that's what y'all doing, right? So, I had to go to the manager and say, listen, this is all part of what your job is. Your job is to understand these medicines, understand how they work, and to be able to actually ensure that you're giving proper delivery to the patients, right? So it's important to understand how these drugs work and to make sure that we move forward in the right way. Yeah.
Just a question. If let's say you are a nurse and the doctor says, oh, give a patient, A, B, and C, and you know that may not be right, but the doctor says, no, give them that. Then if you are a nurse, what is your legal or ethical thing to do if you know, look, man, that's not right?
I want to refer to her.
Call the pharmacy.
There you go.
Call
That
the
was the right
pharmacy,
answer.
get the pharmacist involved, and then usually, most doctors, hospital. The big ones they're pretty good at listening to what you got to say, and then you say, hey, you know what, I called the pharmacist about this. And usually the pharmacist will say, yeah, no, that's not good.
But you always go with your gut, and it's always nerve-wracking, right? If you're a rookie, you're gonna be like, well, am I really right or not? But as you get more involved and you get more understanding of your job, and get more regular usage or understanding of all the different things that happen, then absolutely right. Call the pharmacist. Try to get. Hopefully, you got a good rapport with that doctor. If you don't, then bring in somebody
That's
else.
also the way you approach that.
But you certainly just don't follow because don't become a lemming. I guess is what I'm trying to say. Don't just run off the edge of the cliff because everybody told you to, right? So if you feel like it's a gut problem that's going to cause a problem for that patient, it's your obligation to try to, and if you get told no, you're wrong, then maybe you're wrong, right?
Charge nurse.
Yeah, there you go, chargers. All right, so anyway, so intrinsic resistance. So again, that would be the idea of giving a drug that is going to do nothing to this particular pathogen. It might be a good drug. It might work on a lot of other pathogens, but if that particular pathogen is intrinsically resistant or innate, then it's going to be useless. You can give as much penicillin as you want to somebody with tuberculosis and nothing's going to happen. Bacteria can also develop acquired resistance. And so this was stuff that you learned in chapter 8 when you did your self-study chapter. So there's a little bit that comes back here. So this is the idea that we have two different ways that we can, a bacteria can develop acquired resistance, just like, the adaptive immune system is acquired. In this case, this will be sort of like an adaptation that the bacteria go through. One is spontaneous mutations. Again, bacteria are really good at flipping out a guanine for a thymine or an adenine for a cytosine. They just flip out their DNA nucleotides. And sometimes that'll be enough to allow them to become resistant to whatever that drug is on or whatever that drug might be. So where do we see spontaneous mutations? Think of somebody that has a chronic case of pneumonia. Maybe they're cystic, maybe they already have cystic fibrosis, so they're constantly battling pneumonia outbreaks. Over time, giving that same drug to the bacteria, if I put enough pressure on you, think about it from your own life. If you have enough pressure on you, and there's no way to fight that pressure, but then you'll figure it out. You'll figure out a way around it. You'll figure out a different route. You'll figure out something to get around that pressure. So think about the antibiotic being that pressure down. The bacteria over time are going to sometimes spontaneously mutate to get around that pressure. So this is why it's also incredibly important that we stay on the drugs for the duration. We want to keep that pressure as hard and heavy as possible. So when we talked about before, maybe you get a 7-day regimen of antibiotics, but you only take it for 3 or 4 because you start feeling better. And the odds are in your favor that you're going to continue to improve. But there's also that chance that the bacteria are going to spontaneously mutate. Now they're going to be resistant to that antibiotic that you're on, and now you're going to have to go on something even stronger if it comes back as a secondary infection. Horizontal gene transfer, this is the idea that some bacteria are able to actually move the plasmids. So remember, bacteria have 2 different types of genetic material. They have their chromosome. All right, so this is the bacteria here. So there's its cell plasma membrane. They'll have their chromosome, which is their genomic DNA. All right, so this is genomic. This is all its DNA it needs to just survive, right? In order to be a bacterium, whatever it needs to be able to survive day to day. It's a circular chromosome, right? Bacteria only have one single chromosome. And then we have all these little pieces of extra chromosomal DNA. What are those called? What are they called? Plasmids.
Plasmid, sorry.
Yeah, plasmids. We also call this the pDNA. All right, so plasmids are where most of the virulence factors are located. So the things that allow that bacteria to cause disease are typically going to be found on the plasmids. The thing is, they can do, some bacteria can actually make tens of thousands of copies of that single plasmid. So they have plenty to give away. And so they have the other bacteria that may not have those plasmids, but they still have their genomic DNA. Maybe this guy over here doesn't have any of those plasmids that give it this extra little boost in virulence. So they can do what's called conjugation, right? Or bacterial sex, as I call it. Conjugation. So the plasmids, they'll transfer a couple of these plasmids over to its neighboring bacteria. We call that horizontal gene transfer because it's horizontal. Vertical is mother to child. Horizontal is side to side. So in this case, it's horizontal. This bacteria did not birth from this one, but this one is horizontally gene transferring its plasmid from one to the other. Now, this bacteria has the same exact virulence capabilities as this one. And this is where we start seeing antibiotic resistance pop up the best, or in the biggest numbers is through horizontal gene transfer. So when we look at the mechanisms of the different types of drugs, we're going to cover 5 of them in this chapter. The first one is there's a lot, right? So let's look at the ones that we're looking at. We got cell wall synthesis. There's a lot of them in there. Why? Because that's the best from a toxicity angle. The bacteria, make cell walls. We don't. So there's a lot of options there in cell wall synthesis drug. Protein synthesis. Well, we make proteins. That's going to be going after the ribosomes. But luckily, we'll see as we move forward, the prokaryotic ribosomes are slightly different. And so we still do not have a big toxicity issue when we look at protein synthesis. Then we got nucleic acid synthesis. This becomes problematic because we also multiply our DNA too. Metabolic pathways. There's not a lot, but there's 1 or 2 metabolic pathways that we can attack in some bacteria. And then the cell membranes. This is actually going after the phospholipid bilayer. But we have a phospholipid bilayer too. And so those tend to be the most toxic. So what you're going to see when we go through this chapter is there's going to be a lot of drug names in cell wall synthesis, a few in protein synthesis, and only 1 or 2 in the other 3. Again, because it becomes a toxicity issue. So we can see up here on the list, we got, they're already giving you some of the names there. That's not an all-inclusive, but it's a lot of the different classes of drugs for each of those different mechanisms. So looking at the cell wall synthesis inhibitors, these are going to be, as I've already pointed out, the bacteria cell wall is unique, made of peptidoglycan. We don't have peptidoglycan in any of the human cells, and so it makes it very good, unique target, which is key. Has a very high therapeutic index, so you can eat as much penicillin as you want, and you may get some diarrhea from messing up your normal flora, but it's not going to kill you. So this is the idea. It has an incredibly high therapeutic index. It's not going to cause much harm to the patient. So there's 2 major types, penicillin and cephalosporins. They're both beta-lactam drugs, and so when we talk about beta-lactam, it's important to see how the actual penicillin is formed. So we'll see it on the next slide too. We have this whole molecular formula here for the actual drug, but the key is this square right here that they got lit up. That's what we call it if you're good at your chemistry, organic chemistry, biochem. That's what we call beta-lactam. And so this is a beta-lactam ring that's part of that structure. And so almost every single one of the cell wall synthesis drugs has a beta-lactam ring in it. So they're all derivatives originally coming from penicillin. Then the biochemists, pharmaceutical chemical engineers, they go in and they tweak. They might change. We'll see here on the next slide. They might change a couple things, and it actually improves or changes the way that drug works. But they all have that beta-lactam ring in them. And so it competitively inhibits enzymes that catalyze the cell wall synthesis. So that peptidoglycan on the bacteria, it just doesn't magically appear, right? There's enzymes that come and build that. And so if I'm competitively inhibiting the enzyme, you have to go back and look at your freshman biology, but an enzyme has 2 spots, right? It has basically its structure, and then it has its active site. And that's where whatever it's doing binds into and allows the enzyme to do its job. If I'm competitively inhibiting, what am I doing? I'm going in here and blocking the active site. The enzyme basically shut down. The enzyme can't do its job. The job of that enzyme is to build the peptidoglycan cell wall. And so if I'm blocking it, the bacteria can't do its job. And so this makes most of the cell wall synthesis drugs, they make them bacteriostatic, because they're stopping new growth. The bacteria that's already in your body already has the peptidoglycan structure to it. It doesn't need that enzyme to make the cell wall. It already has it. So that's why it's not going to attack the ones that already are there. That's what makes it bacteriostatic. It's only going to stop new growth. New bacteria that need new cell walls, they're not going to be able to make them because that enzyme is competitively inhibited. So called beta penicillin binding proteins, since there's actually some that bind up to penicillin, and these are going to be potentially useful as a anti-antibiotic. So some bacteria can actually produce these to block the ability of some of these drugs to work. So it makes them resistant. And as I already pointed out, only effective against actively growing cells. So all these are going to differ a little bit in activity. Remember, the gram-positives have their peptoglycan on the outside, and that's going to be a little bit different than the gram-negatives. Gram-negatives, remember, they got LPS on the outside and peptoglycans in the inner membrane. And so in that case, a lot of the drugs are going to be very useful with gram-positives. It knocks out peptoglycan. The enzymes are out on the outside building that peptoglycan cell wall of the gram-positives, and so it's very easy for the drug to get to them and block it. When it comes to the gram-negatives, that drug has to be able to get through the LPS layer, get into the interior portion to block the enzyme to keep it from building it. So a lot of times the gram-negatives are going to be resistant because it's difficult for the drug to get there in the first place. But for a gram-positive, it works out pretty well most of the time. Some bacteria synthesize a beta-lactamase. So remember, when we see these enzyme names, remember if it ends in an ASE, it's an enzyme. And usually the enzyme tells you what it does. And so here it's a beta-lactamase. Well, beta-lactam is the ring, right, inside the penicillin and the different penicillin drugs. Beta-lactamase is an enzyme that goes in, cleaves it, cuts it, basically making it ineffective. If I chop penicillin in half, penicillin can't do its job anymore. And so some bacteria actually have an onboard enzyme called beta-lactamase that it uses to chew up penicillin, thus making it, again, a useless drug. Some of them are going to differ in their names. Sometimes you'll hear it called penicillinase. Gram-negatives tend to produce more of these than gram-positives, probably from some sort of evolutionary background. But that's okay, because we got plenty of drugs out there that we can use in lieu of. Penicillin is not used as much as it used to be. What we do, though, is we take that penicillin, and so your pictures might be a little bit better. Seeing it from the screen might be a little bit easier. But we have the basic structure. The basic structure stays the same in all these drugs. What's changing is the side chain. And so here, penicillin G has a methyl and then has this hexagon-looking chain ring there. That's the original penicillin. And then penicillin V is acid resistant. This was one of the very first derivatives to come out. Acid resistant is important because it helps it get through the stomach acid, get to the intestines. So it's good for a lower digestive infection. And so in this case, what did they do? All they added was an oxygen. And I'm not going to ask you any questions, so don't start freaking out. Oh my God, I got to know all these structures. No, I want you to appreciate how small of changes it is between some of these drugs that you may recognize the name, but then go, wait, that's all the difference is? Well, here, all it is an oxygen between the methyl and the ring. That made it acid resistant. Then we go down the list here, methicillin. Methicillin just has two methyls off of the chain. Dioxycillin, a little bit different structure. Ampicillin, amoxicillin. List goes on there of ones that are all relatively common names for antibiotics. They all come from that original penicillin. So these are what we call the natural antibiotics because they come from an organism. And so that organism was Penicillium chrysogenum. That was the original mold that we discovered. Arthur Fleming discovered that actually became penicillin. These are going to be narrow spectrum, act against gram-positives and a few gram-negatives. And then we go into the ones that we've developed over time. And then they actually have some different capabilities. So when we look at this list again, acid-resistant, penicillinase resistant, methicillin. We hear about MRSA, right? Methicillin-resistant Staphylococcus aureus. Well, all methicillin was a new drug that was developed from penicillin to be penicillinase resistant, to try to get around that onboard enzyme that chews up penicillin. From there, dioxycillin to acid and penicillinase resistant, ampicillin, broad spectrum and acid resistance. So this is one of the drugs that you'll get regularly. As long as you're not allergic to penicillin, they'll give you ampicillin because if you come into the doctor's office, I just don't feel well, and it's clear that you're sick, and they suspect it to be bacterial, they'll probably give you something like ampicillin or amoxicillin because it's broad spectrum and acid resistance. So it'll fight the stomach, it'll get past the stomach acid, and it's broad spectrum. So hopefully, whatever it is that you're infected with will be cleared by this simple drug. Amoxicillin, a little bit more active and less frequent doses. So again, depending on the situation, we can give amoxicillin instead if we feel like the patient's not going to be compliant, or we feel like there might be another beneficial reason you need less of it. It's a little bit more active, but being more active means it might knock out more of your normal flora too. And so there is that yin and yang. So it just depends on the situation. All these things are like she said, things that the pharmacist will know off the top of their head if it's something new and novel use still. So again, we got the penicillin, shared the basic structures we just went through. They're broad spectrum against gram positives and gram negatives if they have that side chain changed, right? Because normally gram negatives are not going to be affected. But some of these side chains that make them broad spectrum then allows them to go after the gram negatives also. Extended spectrum, this is going to push them towards actually being useful against things like Pseudomonas. We haven't really talked about Pseudomonas a lot yet, but Pseudomonas is a pain. Pseudomonas likes living in chlorine. So you will rarely ever find me in a public pool because they freak me out. Because if you got Pseudomonas that can actually survive in chlorine, that's not good. It can survive in mop water, so if you have cleaning agents, Pseudomonas survives in there. Loves hanging out in soil, and so this is why you can't take flowers to grandma after surgery because you'll kill her, because there'll be Pseudomonas in there, possibly get in. So again, Pseudomonas is a pretty nasty bacteria, gram negative, is able to make the, I can't remember the name of it right now. Oh, well, it's able to make the little, it has capsules and things like that. That's what I was looking for. It makes biofilms. That's the word I was also looking for. So Pseudomonas is pretty nasty. It's really difficult to get a drug to it. But some of these have been changed. That side chain has been changed a little bit. That allows it to now be extended spectrum and go after Pseudomonas too. And so what we're trying to point out here is not necessarily to sit there and memorize every single one of these, but recognize the benefits that changing just a little bit actually do. Suddenly made it broad spectrum, suddenly made it acid resistant, suddenly made it extended spectrum. But there's a lot of work that goes behind that at a research level to actually truly understand that, to be able to bring that drug to market. All right, so then switching gears away from the penicillins, but also focusing on the cell wall synthesis, we got the cephalosporins. So there might be a couple drugs here that you recognize. These come from a different fungus. So the first fungus was a penicillin fungus, right? This one is a different fungus called Acronomium cephalosporium. And this one is going to have slightly different effects. But at the end of the day, these are just weapons. Just always remind yourself that these are weapons that the fungus actually makes to protect itself against these protect itself against these bacteria from infecting them or causing them to be destroyed. And so here, that's why it's important to have a different class of drugs coming from a completely different fungus. Chemical modifications have led to 4 generations. Later generations are more effective, as you would suspect. So first generation drugs, we talk about first, second, third generation. Now we got 4th generation drugs. Why are we talking about those? Well, because we don't want to go straight to a 3rd gen drug if we don't have to. There are going to be certain cases if somebody comes in uber sick, they've been fighting it for 5 days at home, and they're coming in on death's door, knocking on death's door. Well, we may have to go straight to vancomycin, put the IV straight into their right into their artery, and hopefully try to wipe it out. But if you come in, you're just feeling a little sick, or it's a minor infection, we don't want to go straight to 3rd gens. We want to go to 1st, then move up to 2nd, move up to 3rd. If that is the way that we can go. So here, the later generations are more effective, resistant against beta-lactamases, but they may have toxicity issues. So we always got to think about all these things. Carbinums and monobactams resist beta-lactamase. Carbinums that have a really wide range of effect. And then sometimes we'll use monobactam, which is useful against digestive diseases. So the Enterobacteriaceae, that's E. coli, Salmonella, the digestive diseases. So Each of these have their own place, depending on how effective they are against what that person might be, what pathogen that person might have. Here's the big one, vancomycin. So we have, the traditional route for somebody that comes in with a staph infection. If you can try a first-gen drug, great. Second-gen drugs are methicillin, third-gen vancomycin. And so, people get all up in arms, a little nervous at vancomycin. Oh, we got vancomycin-resistant Staph aureus out there now. It's scary. But reality is it's scary for that patient that has it. But for the most part, it's not one that we see actually spreading too much just yet. But how does vancomycin work? What makes it such a powerful drug? Not much, actually. Blocks peptidoglycan synthesis just like all the others. It's going to bind to the peptide side chain. So remember, peptidoglycan is made up of two molecules, NAM and NAG. So basically, just these two molecules back and forth. So it's blocking NAM from being able to bind. So it's essentially the same. But why is it one that we wait till the last second to give somebody? Is what the next bullet's telling you. It's an IV drug. You can't give IV at home, right? You can't just say, here's an IV bag and a needle, go do this at home. You'll be fine. It's not going to happen. So in this case, when you keep vancomycin as a last resort drug because it is an IV, requires an IV. Why does it require an IV? Because it's very poorly absorbed by the intestine. So I can't give it as a pill you can take by mouth or any other sort of route because, again, it's not going to be absorbed by the intestine. So I have to put it straight into the bloodstream. And in that case, we're usually going to save that as for somebody that's already going through the gambit, or maybe it's switched over and now they're septic. We'll switch over to vancomycin. Now, it is a drug of last resort, but these slides are about 5 years old now. There are new drugs that have come out. So vancomycin is no longer a drug of last resort, but they're expensive. So it becomes a cost issue too. Which I hate the fact that our medicine is based off of cost, as I think everybody is. But at the same time, it is still, a business. It's not something that you're just given. So there is this cost analysis that goes into it also. Bactitracin is something you probably have in your medicine cabinet. Bactitracin is very, very toxic. So you can't take it orally. You have to only use it topically. Topically is just putting it right on your skin. And so this is going to be things like Neosporin. So things like Neosporin, if you ate Neosporin, you'd be very sick. You're going to be in the hospital anyway. But again, it's just an antibiotic. It does the same thing. It's just blocking cell wall synthesis. And so it's useful if you have a skin infection, right? Why take a pill that has to go be digested in the stomach, be absorbed by the intestine, get into the blood to hopefully make it up to your skin, when I could just give you a topical application that puts the drug straight onto the bacteria and hopefully clear it out. Problem is, if I try to use that drug as a oral, it'd make you very, very sick. All right, so then we move over to protein synthesis. And so this is going to be looking at stopping any of the sort of proteins that are important for you think about things that are important for the bacteria to survive. So it could be proteins that are embedded on the genomic DNA. It could be proteins that are embedded on the plasmids. It doesn't matter. The ribosome is important for synthesizing them all, because we have to remember how does the essential dogma go? We have DNA, right? It's transcribed into RNA, and it's translated into proteins. And this translation event all happens in the ribosomes. Right, so if I have a drug that blocks the ribosomes, that bacteria is not going to be able to produce any of its proteins that it needs. Therefore, it's just going to die. It's not going to be able to survive because it's not able to produce any of the things it needs to survive. So all cells synthesize proteins, every single cell on Earth, because they all follow the essential dogma, DNA, RNA, protein. So all cells synthesize proteins, and so we can block this. The problem is we have to make sure it's not toxic, since all cells produce protein. So this next part here is important for understanding the mechanism of action. we have these numbers. These numbers relate back to a historical way of measuring ribosomes. It's historical, like a total of like 90 years old right now. But Svedberg was the person that came up with this unit. And so that's why the S is there. I'm not asking you to remember this, but the person's name was Svedberg. I think it's Svedburg. And so that's where this S comes from. It's after these numbers. And then it's just a way of measuring, just like pounds, ounces, cups. Svedberg was a way of measuring ribosomal weight. Well, what we've discovered when we looked at the difference between eukaryotic ribosomes and prokaryotic ribosomes is that there's a slightly different weight to the prokaryotes. Prokaryotes have what we call 70S ribosomes, and eukaryotes have an 80S ribosome. So the eukaryotes are slightly different. Good. That makes for a good target because we want the target to be unique for a drug. And so here now we actually have a slightly different, slight difference between eukaryote and prokaryote ribosomes. Now, problem though is for toxicity issues is that we have to remember what's called the endosymbiosis. That is the idea that the mitochondria and chloroplast came from a bacteria probably at some point. The larger bacteria digested the smaller one, but recognized that it was actually producing a lot of energy and kept it on board. And so mitochondria, if you don't remember this from freshman biology, mitochondria have their own DNA and actually make their own proteins. So therefore, inside the mitochondria, they actually have their own ribosomes. The ribosomes are 70S because, again, it backs up the theory that mitochondria were at one point a bacteria. Yeah.
So, to inhibit the protein synthesis and inhibit
Blocking the ribosome with this class of drugs that we're getting ready to go over right now. The last class of drugs we went through was blocking the cell wall synthesis. This class of drugs is going to be blocking the protein synthesis. But these are going to start having toxicity issues because of that fact that the mitochondria inside our cells has a 70S ribosome. And so we might get some toxicity from them. But for the most part, these drugs are going to be relatively benign in terms of toxicity. But we will see there's a couple that are a little wild. So the aminoglycosides, these are going to irreversibly bind to the 30S. So let me back up real quick. Ribosome looks like a sandwich. It has a bottom layer, it has a top layer, and whatever you're putting on your sandwich, think about that as the RNA. The RNA goes in the middle, it reads it, and it starts producing the protein coming out of the side. So in this case, there's going to be two parts. There's the 30S, that's the bottom. And if it is a prokaryote, it'll have a 40S on top. So 30 plus 40 equals 70, right? And this one is showing you eukaryote. It's showing you 50 and 30 having an 80. That's all together.
Is the 30 constant or you doesn't change?
I mean, that's a good way to, for our purposes, yeah. There are some subtle differences, but that'd be if you got into becoming a molecular geneticist. But yeah, it's very, very slight differences there between it. 30S stays the same. It's the top portion that changes. So when we go to this first one, the aminoglycoside, you see it irreversibly binds the 30S. So it's binding the bottom portion of the ribosome. And so this causes it to distort and malfunction. So what's happening is the 30S gets stuck in place. The top of the sandwich slides off. And basically it distorts and the ribosome can't work anymore. And so when that happens, it's going to block the initiation of translation. Just remember that that's what these terms are here, right? We have DNA to RNA, that's transcription. Right? Running out of space. So transcription is DNA to RNA. It's called transcription because we're just transcribing. So if I ask you to transcribe something, I'm asking you just to rewrite it, right? So in this case, we're going DNA and RNA is both made of nucleotides. So think about it that way. We're going nucleotide to nucleotide. I'm just transcribing it. So that's transcription. RNA to protein is called translation. When I'm translating something, I'm going from one language to the next, right? So RNA is made of nucleotides. Proteins are made of what? Amino acids. So that's two different languages. So we call it translation. So I just want you to make sure that you understand what these PowerPoints are telling you, especially if you're using my PowerPoints as your only study guide, which I told you not to do. Here, irreversibly binds to 30S. So it holds it, grabs it, holds it, and therefore it causes distorted malfunction, blocks the initiation of translation. So no translation can happen because that ribosome is basically frozen, stuck by this drug. Causes misreading of the mRNA. So in this case, it misreads it because if the top's going faster than the bottom, if you remember back to your freshman biology, every 3 nucleotides equals an amino acid. So if it's misreading them and you're reading them out of place, then the protein is never going to be made right anyways. So both of these are good from our aspect of trying to kill this prokaryote. Is that if we can block translation altogether, great. And if it is already starting translation, if it's already started, it may start misreading it, great. Either way, whatever that ribosome was supposed to be making, it's not going to make it. They're generally ineffective against anaerobes. All right, so anaerobes, these are going to be the Clostridiums, also some of the bacilli, depending on which ones we're talking about. So again, these are where it becomes important as he was asking, well, what if I think this, but the doctor says something else? All right, well, you get the third person involved and the fourth person involved. Because sometimes these little subtleties are a big difference in the outcome for that patient. So while aminoglycoside may be the right answer, but then they're infected with an anaerobe, well, then it's a useless drug to give them. So interior cauci, these are going to be your digestives. That's also the same spot that the Clostridiums tend to infect. And so this is a big deal, just to understand how some of these drugs are not effective. It's often toxic, but it's generally going to be used when alternatives are unavailable. Why is it toxic? Because again, it's binding to that 30S, and as she pointed out, both prokaryotes and eukaryotes have a 30S ribosome, or portion of the ribosome. So one of the ones that's very specific when there's no alternatives available is what's called tobramycin. Tobramycin is administered via inhalation. So it's going to be one that's used with the mask. And so the patient breathes it in. And this is going to be restricted to people with cystic fibrosis that have recurring Pseudomonas infections. And so this is going to be useful for them. But it wouldn't be something that you just prescribe generally to everybody. This is going to be something that's going to be prescribed after a patient has been dealing with cystic fibrosis and all the side effects of cystic fibrosis for years. And maybe the drugs they were taking, now the Pseudomonas has become resistant to. And so in this case, they might move them up to tobramycin, but this is going to happen inside outpatient clinic or something where they're going to come in, take their medicine. They might get it, if they're had it in home care, they might be able to get it there too. Next group is tetracyclines. Tetracyclines are bacteriostatic. So remember, it just stops new growth from happening. It's going to block the tRNA attachment. So tRNAs, what are they doing? What's the T stand for? Anybody remember? Transfer. What are they transferring? Amino acids, right? So they're bringing the amino acids. That's why it's important not to just use the slides, right? So the tRNA is bringing the amino acids one at a time to the ribosome. If the ribosome cannot get the tRNAs to bring amino acids to them, can they make the protein? No, it's basically like shutting down shipments to the factory. The factory, everything's there. The factory's working fine, but if it's not getting all the shipments of products it needs to build whatever it's building, it can't do its job. So shutting down, blocking the tRNAs from attaching to the ribosome will basically stop the protein from being built because it can't get the amino acids it needs. This particular class of drugs actively transported into the prokaryotes, but not animal cells. So this makes it less toxic. It gets whatever mechanisms. Again, we don't get into all the pieces and parts of how these drugs work. But in this case, just the idea here, actively transported into bacteria, but not eukaryotes is another way to think about that. So this makes it a little less toxic. The glycosylins are related. They're smaller, same mechanism of action, wider activity, but there's a lot of bacteria that are already resistant to them, and so this becomes problematic. There's also this problem with spontaneous mutations. If I put the bacteria on a Petri plate and I give them some of the drug, and it stops them from growing on the Petri plate for a couple of days, but all of a sudden at day 3 they start growing again, that's a pretty useless drug, right? Because, it stopped it briefly, but it didn't stop it all the way. So that's what we're saying here. Wider activity, this is a good drug, but it's against a lot of different bacteria that are already resistant to tetracyclines, because tetracyclines sometimes have a bacteria that are intrinsically resistant or spontaneously mutate around it pretty quickly. Right now, there's only one that's currently approved. Again, when you're studying these, because we're getting into the weeds now of all the different drugs, when you're getting into this, remember, I don't ask minutia questions. Hopefully now 2 exams in, you're starting to realize that if you stay on topic and you go, okay, what are the major classes of drugs? What are the most popular? And when you're looking at these different drugs, what makes that one better than this one? Not necessarily looking at the mechanism for every single one, because you'll get into that. You'll get plenty of that when you take your entire semester of pharmacy that they require after the nursing school. I think I actually got 2 semesters or two portions of it. So you'll get plenty of this, and you will get into the weeds of how all the drugs work. But this is just kind of your very first taste of it, so don't get into all the little minutia pieces or you go crazy. All right, so macrolides, these are a pretty popular class of drugs. Prevents continuation of translation. So same thing, they're all shutting down translation at some point. These are going to be the drug of choice for people that are allergic to penicillins. So we're at a completely different class of drugs. Nothing related to penicillin, because remember the amoxicillins, ampicillins, methicillins, all related. So if you're allergic to one, more than likely you're allergic to all the others too. That's why that question is on an intake form. We need to know, because the last thing we want to do is do what they did to my friend and give them a drug that is going to actually cause their immune system to be even more stressed out, when they might be trying to deal with something else. So the macrolides are important for people that are allergic to penicillin. There's one here that we cannot use called chloramphenicol. I use it quite a bit in the laboratories. It's a great drug to keep out any sort of bacterial contamination of whatever I might be growing. But it is incredibly dangerous to give to a patient because it has a rare but lethal side effect. It's called aplastic anemia. So when we have aplastic, that means it's not the proper shape. Anemia means you have low count. So here, aplastic anemia is the inability to form proper white blood cells. So if I give somebody that has an infection chloramphenicol and they develop aplastic anemia, that's like double, basically stabbing them again. Hey, come into the clinic here. We'll help you out. No, not really. I'm going to kill you. Essentially is what that's saying, right? Because they need their white blood cells to fight off whatever the infection is. And if this drug is used and they develop this side effect, well, then they're dead anyways, because their white blood cells aren't able to fight off and they're going to end up having a problem. So chloramphenicol is a good drug, in the labs. It's a good broad spectrum drug. We use it for a lot. But, when given to people, it's kind of used as a last resort. So again, somebody comes in and they have an infection that nothing is working on. We may give them chloramphenicol because at that point it's a life or death situation, right? The chance that they might get a rare side effect is pretty minor compared to them dying anyways, right? So we might try to chloramphenicol as a last-ditch effort, but it's certainly not going to be one that's given as a first chance. All right, so then we just go through some others here. There's nothing that's terribly exciting about any of them. Leukocinamides are going to bind the 50S ribosomal unit, blocks continuation, inhibits a variety of gram negatives and gram positives. You got and these are all just classes, right? The class is going to be the protein synthesis inhibitors, and then these are different groupings underneath them. The next one, also bacteriostatic against gram positives. Streptogranums are going to be useful because it is actually 2 drugs together. And so this is what we start seeing more and more happening now, is these synergistic drugs, is that, if we have a problem, as I just said, one drug within a couple days may have bacteria growing on the Petri plate again. That one drug was pretty weak. The bacteria figured out a way to spontaneously mutate around it. I add a second drug. Now we're attacking that bacteria from two different vantage points. The bacteria is not going to be able to spontaneously mutate as quickly. We'll have some slides on that next Thursday when we come back. It's going to be stuck. It's going to have to, it'll basically succumb. So what we see now happening with a lot of these more dangerous bacterial infections is that we give more than one drug. We give 2, 3 sometimes to minimize the chance that that bacteria becomes antibiotic resistant. So if we're hitting it with multiple different angles, we're going to minimize the chances. So here the streptogramins are going to be 2 drugs given a synergistic pair called Synercid. One individually, if I gave each of those drugs individually, they're bacteriostatic. So they're stopping growth. If I give them together, they become bactericidal. And they're good against gram-positives for the most part. So this is how we start seeing medicine evolving. We're starting to see it go from being a single drug. Here's a Z-Pak, of basically amoxicillin, and then now we're switching over to where some of these drugs are actually double and triple to ensure that we, 1, minimize spontaneous mutations, and 2, if you have 2 weak drugs, maybe they're actually stronger if we give them together. All right, so then we switch over. So those are the protein synthesis ones. We still got a few minutes here, so we'll go through the nucleic acid synthesis because there's not very many of them.
Good question. Okay, so if you put 2 weaker drugs together, would they typically be from a different derivative, like one for cell wall versus one for
You could.
ribosome?
That would be useful for the most part. Yeah, they do both. They do both, but there would be usefulness to that because you're attacking it at 2 different spots. Either you can attack it from 2 different spots, or you can attack the same spot with 2 different drugs. And both of them have, again, there's no way. It's like each drug is almost comparing apples and oranges. There's no way to really truly compare this one versus this one. And again, now we're getting into personalized medicine issues too, where these drugs may be great for you, but not for him. And so. It becomes very difficult. If you're being confused by the slides, imagine being, in the hot seat trying to figure out which drug is the best one to give. It becomes very problematic. All right, so we only got 3 drugs that inhibit nucleic acid synthesis. Why? Because we do that, right? So this is going to be during mitosis, right? If you remember back to your mitosis in the cell cycle, you had G1, right? Gap phase 1, you had synthesis, or S phase. Well, remember what is synthesis? What are we synthesizing? DNA, right? It's when the new DNA is being made for the new cell. When that cell is going through replication, it's got to synthesize, or it's got to make a copy of its genomic DNA and all its plasmids. So when it goes through binary fission, each of those bacteria have the exact copy of the DNA. Well, unfortunately, our cells go through that same process. G1 to S. G2, mitosis, and then cytokinesis. So right here, you got fluoroquinolones. These are going to inhibit topoisomerase. So topoisomerase is the enzyme that keeps DNA from supercoiling. So you have to take a look, go back and look at what that means. But remember, DNA is a double helix, sort of like a spring. And if I unwind a spring too much, if I keep unwinding it, it'll actually start spiraling the wrong way. And when that happens, especially the DNA, it's destroyed, it's damaged. And so if I can actually block that enzyme from doing its job, I could potentially have quite a few of the bacteria, when they're going through a cell cycle, they're going to have their DNA damaged and it'll die. So here, fluoroquinolones are great for blocking topoisomerase, blocks it from being able to multiply correctly. So that's what it says, enzymes that maintain supercoiling of DNA, that's topoisomerase, the drug's blocking that. Bactericidal against a wide range of bacteria. Why is it bactericidal? Well, if I destroy your DNA, you're dead, right? So in this case, that makes sense for it to be a bactericidal drug. If I block the topoisomerase and it's not able to replicate its DNA properly, it's done. Rifamycin, this is another one of those drugs that the bacteria is really easy to get around. Rifamycin was actually one I was thinking in my head when I said I could put it on a Petri plate, and within a day or two, I'll have some new colonies already popping up. This is going to prevent initiation and transcription. So then we're going DNA to RNA. Bactericidal against gram-negative, some gram-net positives, and mycobacterium, so that's good. But resistance develops pretty quickly because the enzyme that's doing transcription is called DNA. DNA, it's an RNA polymerase, I'm sorry. So it's polymerizing. Polymerizing means to make. Making RNA, that's only happening during transcription, right? So here it mutates. The bacteria is able to mutate its RNA polymerase pretty quickly, and it gets around rifamycin. So rifamycin is a good drug to give in combination. So when we start getting into the different disease chapters, the way that the different disease chapters work, and I'll point out when we get to it, is that it shows you the name of the drug, tells you the signs and symptoms, tells you the mechanism of action, essentially mechanism of pathogenicity, and then it tells you what drugs are available against that particular disease. And so that's where a lot of these are going to come back to play. So we'll see rifamycin as a drug that's used, but we'll see that's done in combination because rifamycin is easy to get around by the bacteria by itself. And then you got metrodiazoles. These are only going to be 2 anaerobes. So again, somebody comes up with a Clostridium infection of some sort, whether it be difficile, C. diff, botulinum, or tetanus. This is a good drug to give because it affects the anaerobes. And anaerobes are a completely different beast than most of the bacteria that we deal with. All right, so I will leave you with that because we're out of time. So let me hit the stop record button. But what I will be doing, and I want you to